Okay. Hi, everybody. Welcome. I think now's a good time to get started. We're very happy. My name's Adam Smith. I'm one of the co-organizers of the summer school, along with Madhur and Shuchi and Ran, whom you've met before. We're very happy to have Antonio Blanca here giving one of these little courses. So Antonio is a professor at an assistant professor in the computer science and engineering department at Penn State. Before that, he was at Georgia Tech, and then before that at Berkeley, UC Berkeley, and before that at Georgia Tech again. He works on his research is on a variety of topics around randomized algorithms, and especially this area of sampling using Markov chains that he'll explain. And he teaches classes on that, as well as core algorithms classes of the kinds you guys have taken before. So we're delighted to have him. And Antonio, with that, I'll hand it over to you.
Thanks for the introduction, Hans. Okay, I have one small request for you before we start. If you can turn more videos on, that would be great. Otherwise, I will be looking at the same two faces for the rest of the lecture. Thank you, guys. Yeah. Okay, so I'm going to start with the problem that is going to motivate the Markov Chain Monte Carlo method, right? Before we even get to define Markov chains, let's start with the problem. So here it is. So it's quite a natural problem, right? So we're going to have a finite set, okay? So and we're going to have a probability distribution over the set. Okay, so that means that every element of the set is assigned some probability phi of x, and let's suppose that we know it for now. Okay. Okay, so what is the problem? The problem is that we want to draw samples from this distribution, right? We want an algorithm to draw samples from pi. Okay. So, okay, is the problem clear? Okay. So, yeah, so this is a fundamental computational problem. I don't know if you've seen it before. I guess that in most research areas in computer science, engineering, and other applied sciences, it's hard to go by without encountering this problem, right? In some form. So we have some probability distribution. We want to draw samples from it efficiently, and as computer scientists, we would like to design this type of algorithms, right? So first, before we get into the MCMC method, which is a type of algorithm for precisely solving this problem or attempting to solve this problem, I wanted to give you an idea of why this is hard, right? Because there is this notion that this might not be hard, right? Like, okay, I have a dice, okay? I have 6 possible outcomes. I know the probability of every outcome is 1/6. You know, sampling is just you generate a random number and map it to the different possible numbers, and you output whatever, you know, based on the random number that you got. So yes, when the finite set here is small, when we know the probabilities, this is a simple problem. Things get more interesting when this set is huge, and sometimes we don't even know the probabilities exactly. We don't know, we have an implicit definition of the distribution, but not an explicit definition, okay? So let me give you a concrete example here, right? Now, suppose that we're given a graph, right? And let us consider the set of all the independent sets of the graph, right? So now we define this set. It's all independent sets of G. Should I define what an independent set is? You guys okay? Like, for those of you who don't remember, this is a subset of.
Can you explain what you mean by independent sets of a graph?
Definitely, right. Do you see the board now?
Yeah.
Okay. So yes, let's do that. So all the independent set of the graph. So let's define what an independent set is, right? So we have a graph, right? So with a vertex set V, and it's a subset of the vertices. It's an independent set.
Apologies for interrupting, but do you know if this is still recording?
It shows
My
recording.
It is,
understanding
the
it's
red
recording
lights in the corner.
automatically.
All
Yeah,
right,
it's recording. Yeah,
thank you.
yeah. It's an independent set. If there are no edges that have both endpoints in I, right? So has both. I mean, I'll give you an example now. Right. For example, if your graph looks something like this, right? So an independent set would be, for example, you take this vertex and this vertex, right? Because you see there are no edges between these vertices, so this is an independent set. But if you were to choose also include this one in the set, then this is not an independent set because now you have like internal edges to the set. Okay. Yeah, feel free to stop me and ask me for these kind of things because some of you may know, some of you may not know, some of you may have forgotten what it is. So it's fine to interrupt. Okay. So now you have a graph. You look at the set of all the independent sets, right? So for example, there could be many of them, right? If you have a bipartite graph with n vertices on one side and vectors on the other, any subset of one of the partitions, right? One of the partite sets is an independent set. So you can have many of them. Right? So the distribution that we're after here is the uniform distribution over all the independent sets, right? So every independent set receives the same probability, right? So that means that for every independent set in omega, we assign probability pi of I equals 1 over the number of independent sets. Okay? And now suppose that we want to sample from this distribution. Now the problem is much harder, actually much harder, right? So first, notice that this here, you can have an exponential number of independent sets, right? So first, the set space is exponential on the size of the graph. So really, you should not be trying to list all the probabilities, right? In this case, there is only one, but you cannot list all the independent sets and write the probability next to it to sum, right? You cannot do that. You cannot take that approach. But even more dramatic is the fact that computing this is very hard. Computing the number of independent sets is sharply hard, right? And those of you who haven't seen this class, this is a class that is harder than NP complete problems, right? So this is not decision, this is counting, which is harder than decide, right? So computing the number of independent set of a graph, it's an insanely hard problem, it's sharply hard. And still, this is a problem that we want to address. We want to sample from this distribution, right? So we cannot do it exactly because it's a hard problem, but the hope is that we can do it approximately, right? That we can generate samples from the distribution with an algorithm that is producing samples that have high quality and a small bias, right? So notice here that to define this distribution, we only need to provide the graph, right? So we want to algorithms that run in polynomial time in the size of the graph, even though the set of the distribution, the support of the distribution omega is going to be of exponential size, right? Okay, so this is just a motivating example, and what you should get from this is sampling is important and sampling is really hard. Right? It's not a simple problem, right? And that's why we turn to this class of sophisticated algorithms called Markov Chain Monte Carlo. Okay, so now let's start the lecture with a brief introduction to Markov chains. After that, we will study convergence properties. In particular, we're going to study these Markov chains and see the long-term behavior when you go to time goes to infinity, to what distributions these Markov chains are approaching. And the goal then is to show you the two main techniques that we have, or the main two classes of techniques that we have to analyze the speed of convergence of Markov chains that are going to determine the efficiency of Markov chain Monte Carlo algorithms, right? So let me give you now one example of a Markov chain that maybe you've seen before with a different name, or okay. So consider a directed graph, weighted, right? A weighted directed graph, right? So let's take a simple example, A, B, and C, and let's assume that we have directed edges. So do something easy. Okay. Now we're going to put weights, but these weights are going to correspond to probabilities, right? So from a vertex, we're going to say, okay, I have probability 1/2 of going to B from A and probability 1/2 of going to C. Let's say that from B, I have probability 3/4 of going to A and probability 1/4 of going to C. And from C, I have probability 2/3 of going to B and probability 1/3 of going to A, right? So now this graph encodes some Markov chain. The other thing that we need is some starting point. So we say, okay, we're going to start at vertex A of this directed weighted graph. When we're at A, we're going to flip a coin, right? If it heads, or we pick a random number. If it's less than 0.5, we go to B. If it's more than 0.5, we go to C, right? Now let's say that we went to B. Now we're at B, we flip another coin. And now we have probably 3/4 of going through A. So if the random number is between 0 and 3/4, we go to A, otherwise we go to C. And we repeat this many times, and then we can ask questions, okay, after 100 steps, what is the probability I'm at C? Or after 1,000 steps, what is the probability of being at B? Okay, there's some questions in the chat. But I think the TA start taking Sharpie. Okay, so I guess this is being answered. So yeah, so I meant Sharpie hard, which is the class of counting problems, right? So which is counting all independent and Sharpie hard. Okay, good. So there's some useful discussion in the chat. If it needs my attention, let me know. I won't be paying attention all the time, but every now and then I'll take a look. Okay. Okay. So this is an example of Markov chain, and of course you can change the weights here, change the graph, and all this would be this is the type of Markov chains, right? Kind of an important type. I'll come back to that later. Okay. So here is a different class of Markov chain. Look, they look a little different. Okay. So okay, so I'm going to be writing that. This is another Markov chain. Okay, and now this is these are random walks on an undirected graph, right? So this is probably something that you may have seen also. So we have a graph, let's say finite undirected graph. So at time t, suppose that we're at some vertex of the graph, right? Suppose that we are at I don't know, some vertex v sub t of the graph, and what we do is we're going to take a random step, right? So we're going to look at all the neighbors of that vertex, and we're going to pick a random neighbor and go there. Okay? And after we move, we're going to repeat the process and repeat. This is a Markov chain also, right? This is a random walk on the graph, but this is also a Markov chain. So from BT, pick a random neighbor or a neighbor of BT uniformly at random. and go there. Right? So, for example, if your graph looks something like this, you see, like from every vertex, you have probably 1/2 of going to one neighbor, probably of 1/2 of going to the other neighbor, because every vertex has exactly 2 neighbors, right? So if you were to write this as a directed weighted graph like we did before, right? Then we have weights 1/2 everywhere, right? Right. So then, and there are simple examples, right? So any graph will yield some random walk on the graph. By the way, random walks is on graph is a very important primitive, and they're very heavily stored in theoretical computer science and other areas, right? You know some algorithms. There's some famous algorithms that use random walks. Do you know one? Can you tell us? So PageRank, right? From Google search. So they do random walks on the internet graph to determine which pages are more important and which one are easier to get to. And so they're doing random walks to create these rankings, right? So yeah, they're an important primitive, and they are a type of Markov chain, okay? So yeah, I wanted, before giving you the definition and going from there, I wanted to give you 2 examples that you may have seen before. So any questions? No? Okay, so let's now give you a definition of a Markov chain. Okay, so we're going to take, let omega be a finite set. We're going to call it a state space. And we also have a matrix, let P be a matrix of dimensions omega by omega, indexed by the elements omega, such that the entries of this matrix will give you the transition probability, right? So P is called a transition matrix, right? And the entry XY will tell you what is the probability that if you are X, we go to Y, right? So this is probability of going to Y from X. Okay. So usually, okay, so since the important thing here is the state space and transition matrix, right? So usually we say that the pair omega P is a Markov chain, right? So couple of notes here, right? So if you look around and now you open Wikipedia and look for Markov chains, this may not be the definition that you find, right? This is not the most general definition, so, and perhaps not the most standard, but it's a fairly common one using in TCS, in theoretical computer science, because we're working with discrete spaces. So some things that change that would make this definition more general is that we don't really need to impose this finite condition on the state space. You can be thinking of infinite but countable state spaces. And also, we are here implicitly saying that this matrix P is going to use at every time step, right? But we don't need to do that, right? We can use different matrices at different times, right? So instead of being a time homogeneous process, it's a time inhomogeneous process, right? So you can also define, you can also allow for this generality for when you define Markov chains. Okay? So there is a question. Go ahead. Yeah, feel free to interrupt.
Yeah. So can we say that a Markov chain is a tuple, or not a tuple, a pair of the omega and p? So
Yes. So as far as if we think of omega as a finite state space, that this is required, right? Because if it's not finite, you cannot define the matrix, so it would be an infinite matrix, right? So yes, you can define it like this, as a tuple, as a pair of the state space and the matrix. And what I'm getting at is that this sometimes you can define it in a different way. So let me give you one key property that this process has, right? So the key property is what is called the Markov property, hence the name. So essentially it says that the location at time t+1 only depends on the location at time t. Right? It doesn't matter how the process got to time t. To determine the location at time t+1, all that you need to know is the state of the chain at time t. Right? So if you condition on the behavior from time 0 to time t, is the same as conditioning on the behavior just at time t. Right? So the location of the chain at time t+1 depends only on the location at time t. We say good time here twice. Okay, so and if you look at our previous example on the graph, like let's say take the random walk on a graph, just knowing where you are right now, the vertex that you are, it's sufficient to say to know where you're going, right? So from that vertex, you now pick a random number, and you will pick a random neighbor. Okay, so this is the Markov property, and more generally, if you have a sequence of random variables that satisfies this property, that the xt+1, for those of you who are perhaps a little bit more advanced with probability, if you have a sequence of random variables and the state of xt+1 depends only on xt, right? Then this sequence of random variables is called a Markov chain too. Okay, but for us, let's think of this concrete definition. We have a finite state space and a matrix that is given us the transition probabilities. Okay, any questions? Okay, so one immediate thing here that we can do is that we can take, say, the example here from the beginning, and just to make sure that we're on the same page, we can write the transition matrix, right? For this Markov chain. I said that this is a Markov chain, so we should be able to write the transition matrix. And let's see if I can. Yeah, a little out of practice with the online stuff. Okay, so here is the Markov chain that I defined verbally. Now in our definition, we're going to have a state space. What is the state space in this case? Well, we have three vertices, right? So there are three states. So it's going to be A, B, or C, right? And now there is going to be a transition matrix that is going to tell us the probability of going from A to A, from A to B, from A to C, right? So we have a matrix here. It's going to be a 3x3 matrix, and we can index this matrix with the elements of the sets, as we said. So the probability of going from A to A is 0, from A to B is 1/2, from A to C is 1/2, and now you get the idea, right? From B to A is 3/4. You get a 0 here. From B to C is 1/4. C to A, 1/3, 2/3, and C. Okay. So this pair here of the state space and the transition matrix define these Markov chains, right? It's another way of defining this Markov chain that I draw there, right? So one observation here is that notice how, if you look at the row sums here, they are up to 1. Okay. And that's kind of necessary, right? Because from a state, you need to know all the exit probability, right? So you need to know what are all the possible options, and they need to add up to 1, right? Because it's a probability distribution over the possible transitions, right? So P, the row sum of P is 1, and that's why P is called an stochastic metric, right? P is called an stochastic metric. Because its row sum are all 1. Right? So what I mean by that is that for every x, you look at the summation over y of pxy, this has to be 1, right? And in words, this says like if we're at x and we sum the probability of all the possible transition, that needs to add up to 1. Right? Any questions? Okay, let me now give you a nicer example, because look, random walks on graph are pretty nice, but here is one that's probably you have not seen, but that you use. So the other example is card shuffling. Okay, so here we're going to set omega to be the set of all possible orderings of the cards in a deck of cards, right? All possible orderings in a deck of n cards, right? I mean, you can take n to be 52 if you want to be the regular deck of cards, but in general, we can say we have n cards, okay? Okay, so what is the cardinality of omega? Yeah, okay. So any volunteers? How many possible orderings?
N factorial.
N factorial, right? So, and in general, well, I mean, this is in general, if we have 52 cards, right? Then this is 52 factorial. This is already pretty big, right? This is like 10 to the 68, right? Roughly. So it's a pretty big. So the number of orderings, the number of permutations of the deck of cards is quite big, right? And when you're shuffling, what is it that you want to do? You want to generate a random ordering. That's what shuffling should be, right? That's your goal when you're shuffling. You want to randomize the deck. So of all these 10 to the 68 roughly possible orderings, you want to pick one at random, right? So that's the goal when you're shuffling, right? So you want to pick a random. So let's look at some silly shuffles first. And these are silly in the sense that they're pretty simple, and they were created because, well, we needed to understand these simple shuffles first before we could understand the harder ones that we actually use, right? When we're shuffling cards, right? So one of them is the random transposition shuffle, right? Okay, so here the idea is that, okay, you have a deck of cards, and let's randomize the deck by picking 2 random positions in the deck, or 2 random cards, is the same. So you say that you pick 2 random cards, 10 of clubs, and a of spades, and you flip them, right? And then you pick 2 random cards and you flip them, or yeah, and you keep doing that. Okay, so that's a Markov chain. Okay? So let me write it here. Pick 2 random cards. I and J with replacement, which means that you can pick both. I mean, you can pick I twice. And then we swap those cards I and J. Okay, so this is a Markov chain. So the state space is a set of all possible orderings. We can write the transition matrix. This is kind of a simple exercise. Probability of going from I to J. So I and J are orderings. Sorry, it's not orderings. Let's say different notation here. So now it's X and Y are two different orderings. And in one move, if the two orderings differ by more than one swap, right, then the probability of transitioning is 0. Right? You can only transition from X, you can only transition with this swap to Y's that differ by only one swap, right? So the probability is going to be 0 if X and Y differ by more than one swap. Another case is when X equals Y, right? Which is the probability that you stay put. Well, in this happens if you select the card X twice, right? So you have to select some card X that happens to probability 1 over n if you have n cards, and then you need to select it again that happens to probability 1 over n. So it's 1 over n times 1 over n. That's 1 over n squared for the n possible cards, right? Then n different cards in the ordering for X, right? So this is 1 over n probability overall. And when the remaining probability, you actually do the swap, right? And that happens with probability 1 over n squared, right? If X and Y differ in one swap. So if X and Y differ in one swap, you need to pick the first card that happens to probability 1 over n, pick the second card that happens to probability 1 over n. So 1 over n times 1 over n is 1 over n squared. And this would be the transition matrix for this shuffle. Okay? Of course, this is one way of shuffling a set of cards. There is another one. So in a random, right, which is essentially exactly what you would guess. You get the top card and you set it in a random position. Take the top card and set it in a random position. And you keep doing that, right? Top card and insert a random position. Okay. Also a Markov chain, so you can write P, right? So P, you can write it. So write P. I will leave this as an exercise. You can do it, similar to what we just did. So you can try. But this is also a Markov chain. Okay, so these are two very simple shuffles, but this is not how you shuffle cards, right? How do you shuffle cards with your friends when you're playing? Okay, so I guess all of you will
take the top half and the bottom half and just try to put them.
Exactly, right? So this is called the Rifo Shuffle, right? And this is what you use and what the casinos also use, right? They essentially, what's going on here? So you try to cut the deck in half, and then you try to kind of mix it, just dropping cards from the left hand, the right hand, and you hope that this process randomizes the deck. And yes, this, of course, the casinos use it, so this has been very well studied. And there is a mathematical model for this type of shuffling. Let's see what I'm adding. So yeah, so here is a mathematical model for this shuffle. Of course, we need to model this. Okay, so what we're going to do is we're going to split the deck. And of course, when you try to split the deck in half, right, you don't count the cards, right? So you try to do it in half, but there is some error there that you may have a little more than half on one hand than in the other, right? So the way this is modeled is to split the deck by choosing from a probability distribution, by choosing L from the binomial distribution. Okay, let's say that we have these two cards. So we're going to take the binomial with parameter 52 and 1/2. Okay. So that's going to be the number of cards that go into your left hand. And then we're going to take R to be 52 minus L, right? All other cards are going to go into your right hand. Okay. So by the way, are you guys comfortable with me saying binomial 52.5? You guys know what that means, or if not, I'm happy to clarify. So, but you need to let me know. Okay. So, okay. So you draw a random. You draw this number from the binomial distribution. Now you have cards on your left hand and your right hand, and now we need to model the mixing part, right? When we draw cards. So, and the way this is done is by saying we're going to repeat while L not equals to empty, or well, there are some card left, right? Either you have cards on your left hand or your right hand. So we now decide if with some probability we draw from the left hand, with some probability we draw from the right hand, right, into the mix, right? So with probability L, number of cards in L, or L plus R, we drop card from left hand, let's say from L, and with the remaining probability, which is R we drop card from R, right? And the intuition here is that if L is much bigger than R, right? This probability here is bigger than this probability here because L is bigger than R, right? So that means that you are more likely to drop from the hand that has the most cards. Okay. So okay, this is a mathematical model, and they say, okay, this is how you shuffle cards, but it's not clear that this is a good model. But it turns out that it is. This is a model that was studied in the 50s by Gilbert, some mathematicians, Gilbert, Shannon, and Reed. This is like the 1950s, 1955. And this is a good model, right? What that means is it's a good approximation of how people actually mix the deck of cards by using the Rifo Shuffle, right? And in a very interesting result, we'll come later to this if we have time. There is the result I want to mention from 1990 by Bayer and Diaconis. It's like 1989 or 1990, something like that. That essentially they show how many times you need to repeat the Rifo Shuffle in order to randomize the decks. Do you know the answer to this? Have you guys seen this? This was kind of a famous article at some point. So it turns out that you need to do 7 shuffles, right? So now you know that when you're playing cards, if you don't do 7 shuffles, your deck is not randomized. And it's really not randomized. It's really far from being randomized. But if you do 7 or 8, then it starts being randomized. Okay? Again, this is a Markov chain, and this result is about studying this Markov chain in order to prove this type of results, right? 7 shuffles suffice. Right? Okay, any questions? Okay, so we're going to be interested in understanding the long-term behavior of a Markov chain, right? So we have a state space, we have transition metrics, and we're going to say, okay, we repeat the move, take many steps of this Markov chain, say 10 steps, 100 steps, 1,000 steps, right? And now we want to understand what is the distribution of the chain, right? What is the probability that you're in a state? What is the probability that you're at some other state? Right? So this is what we're going to do next, right? Long-term behavior of Markov chains. Okay, I can keep going. I mean, I'm not getting a signal of where you have questions, no questions, where this is fine. So definitely stop me if you have if something comes up. Okay. So as I said, what we want to understand here is what is the distribution at time t equals 10, right? Or t equals 100, or at infinity, right? So what do we mean by time? Well, time in terms of Markov chain usually means the number of steps, right? Time 10 means that you have taken 10 steps of the Markov chain, 10 random steps, right? Time 100 means you have taken 100 steps, right? T infinity means, well, what happens when you take time t to infinity? What does that limiting distribution looks like? Okay, so these are the type of questions that we want to understand. They're going to be relevant for the Markov chain Monte Carlo algorithm, right? And here is a quick fact that will help you navigate the notation. Is that okay? So if we let xt be the state of the Markov chain, let's say omega p at time t. Okay, so xt is a random variable, but we know that the probability that xt is equal to x or y, so x, given that x0 is y, right? So this is an important probability. This says at time 0, you were in some state y. Right? Yeah, go ahead.
Okay, so when you say we're in time like t equals 10, does that mean we have already transiting for like 10 steps? Can I understand it this way?
Right. So time means, yeah, I actually should have written it here. So time means number of steps. We have taken 10 steps, right? Time 100 means we've taken 100 steps. And by the way, I should also clarify what I mean by distribution, right? So let's say that we start at time 0, we are on a state. So the distribution is with probability 1, you have the state that you know where you are, and everything else has 0, right? But once you take a step, right, now you have, well, let's say that you don't take a step, but you know that if you take a step, there is chance 1/2 of being in one state or 1/2 of being in the other, and so on, right? Depending on the transition matrix. So when we say what is the distribution at time t, we say, okay, after 10 steps, what is the probability of being in state 1, or the probability of being in state 2, probability of being in state 3, and so on, right? That's what we mean by distribution at some time, right? So use this thing here that I'm writing is useful to understanding that, because the claim here is that this probability has actually a quasi-finite form, right? The probability that at time t, after t steps, we are at x, given that we started at time 0, given that we started from y at time 0, it's given by the matrix essentially. Anyone knows what this is? This is going to be equal to, you look at the tth power of the transition matrix, and you look at the entry xy, right? This exactly gives you the probability of going of, sorry, it should be the other way around, yx. Of starting at y, going for t steps. So yeah, it's wrong in the notes, so I have to fix that. But starting at y and going to x, right? Okay, so this should not be obvious. This is just if you knew it. Right, it's one of the things that people sometimes knows. Right? And the proof of this is by induction. I could do a proof. It's kind of a simple one. You guys want to see it, or you want me to keep going? We won't have time to see many proofs, given that this is only 3 hours to give you a primer on Markov chain. But if you want to see a proof, I can show it to you.
So is this PTYX means that we start from Y after T steps go to X? Did I understand wrong?
Yeah, that's exactly what it is. It's the probability that if you start from Y and you move for T steps, that you land at X. right?
So
So this is what,
what's the difference between the left part and the right part? Is it just different expressions? It's the same expression?
well, this is a probability, right?
Yes.
This is a probability. This is a number, right? This is a matrix P. And I took T powers of that matrix. I took P times P times P times P, right? And then I look at the resulting matrix and I look at that entry, and that entry is given me that probability exactly. Okay, so let's do it like let's do the proof just to get you guys used to the notation and so on, right? So this is what we want to show, the proof by induction. Well, for T equals 1, this is the definition of the transition matrix, right? So the probability that at time 1 I'm an X, given that I started from Y, is just okay. So probability that X1 is X, given that X0 is Y. This is just the transition matrix, right? P of Y to X, right? So the base case of the induction is this is satisfied by definition of P, right? Okay, and now in general, we can do, so this is, okay, so now we open this matrix multiplication, right? So PT is equal to PT minus 1 times P, right? So we open that, we look at the XY entry of that matrix. So this is the summation C over omega PT minus 1. I'm just doing matrix multiplication here. Right? Agree with this, right? So this is some matrix, this is some other matrix. This is going to be equal to some other matrix. And if we want to know one entry, what we do is we take the summation that moves through these guys, and that's exactly what I'm doing there. Okay. So now we apply the induction hypothesis here. Right. So this is going to be equal to the probability that xt minus 1 is equal to C, given that x0 is X. And this probability here, I can conveniently write as the probability that xt is Y, given that xt minus 1 is C. And I can even add here the probability that x0 is X, because it plays no role, right? By the Markov property. Are you happy with that? And now it's just some massaging of this distribution. You group these two probabilities together, right? This is the probability that xt minus 1 is C and xt is Y, given that x0 is X. So these two probability multiply give you this. It's in base rule, okay? And finally, you see that this is just summing over all the possible C's, right? So this is the total law of probability. You get that this is the probability that xt is Y, given that x0 is X. Okay, this is what I wanted to prove. So any questions with this?
Just for like some intuition, can you like kind of think of the stochastic matrix as like the weighted adjacency matrix, and then when you raise it at power, it's kind of like has like a
Yeah, that's a very good way of thinking about it. You have to be a little bit careful, right? Because in the adjacency matrix, you have zeros and ones, right? And if you look at the transition matrix, let's say what you have is 1 over the degree, okay? And the degree can be different. So it's the same. For instance, if the graph is regular, the mapping that you have is exactly correct, right? And if it's not regular, the mapping that you have is not exactly correct, but it's definitely giving you the right intuition, right? If you power the matrix of the graph, the adjacency matrix of the graph a lot, you're counting path, right? So that's more or less what's going on here. Okay.
Thank you.
Yeah.
So just us to make sure, this power notation, is that just pxy, this number to the tth power?
So this power notation is the matrix P raised to the tth power. So you take matrix multiplication T times, right? And after that, you have a matrix, and then you look at the XY entry of that matrix.
Oh, okay. Okay.
Right?
Yeah, thank you.
So here we're looking at the XY entry of the matrix P to the T.
Okay. I got
Right?
it.
And that's why I wrote it like that and so on. Okay.
Yeah, thank you.
Other questions? Yeah, this is good. Keep asking questions. It gives me a good feel of how you guys are following the lecture. Okay. So, right. So that was just a little warm up, right? So there is an important type of distributions when we're studying these Markov chains that are called stationary distributions. Okay. And roughly with words, what this means is these are distributions that once the chain reaches that distribution, it doesn't escape that distribution. Right? So it has some probability over the states. You take one more step, you still have the same probability over every state. Right? So let's formalize that because they're going to be an important class. Right? This is one of the key notions that you should know when you're studying Markov chain. What is a stationary distribution? Okay, so take a Markov chain. Right, so let's omega b be a Markov chain. Right? We say pi is stationary if pi times p equals pi. Right? So let me just do some clarification here. Okay, this is quite bad. So what? Okay, that's the. Okay, so what does this mean, right? So I already said with words, but let's make sure that we understand this, right? We can view pi as a vector, right? Again, indexed by the elements of the state space, right? So the first coordinate corresponds to the probability of the first element of the state space, the second coordinate, and so on, right? So we can view pi as a vector. And here what it says that when we take the matrix multiplication of pi times p, what we obtain is another vector that is, again, pi. Okay? That's what it means to be stationary, a stationary distribution. And as I said, they're going to be an important type of distributions for the Markov chain, the most important ones, because are the ones that are going to dictate the long-term behavior of the Markov chain. Right? When you take it to infinity, you're going to be stuck in this stationary distribution. Okay, so I have an example here. Maybe suppose that this is from earlier. We have this transition matrix, right? So we have this transition matrix. Yes, I may have even used different numbers, but let's use these numbers now, right? So 3/4, 0, 1/4, and then 2/3, 1/3, 0, right? So this is just giving you transitions from A, B, C to A, B, C, right? So this is the matrix P. Okay. So for example, if we take the vector, we look at the distribution pi1 that is 0.2, 0.4, 0.4, which means probability 0.2 in A, probability 0.4 in B, probability 0.4 in C, right? There's a probability distribution over omega of the state space. Then it's easy to check that this is not a stationary distribution. If you do the multiplication, this is not equal to pi1, right? So if you do pi1 times p, what you get is something like, I did the calculation, but it's really far from. So 7/30, then 6/30. Okay, which is not pi1. So this is not a stationary distribution. But if you tried, you can now consider pi2 equals to 22/53, 16/53, and let's say 15/53. And you multiply this times p, which is 0, 1/2, 1/2, 3/4, 0, 1/4, 2/3, 1/3, 0. So for example, if you just do the top entry, what you get is 22 over 53 plus, so that's times 0, so that goes, that's not there. Then you do 16 over 53 times 3/4 plus 15 over 53 times 2/3. And this is what? This is the 4 cancel, so you get 12 over 53 plus 10 over 53, so you get 22 over 53. So you see the top entry matches. And you can check that all the entries actually match. And this is a stationary distribution. Okay. Okay, so just to, since we are, okay, so we are at 2/3 of the time that we are supposed to cover. So far, I have defined a Markov chain, and I have defined this notion of a stationary distribution, right? And now the questions that we should ask is, well, there are a few, right? Is there always a stationary distribution? Is it unique? Does the chain converges to a stationary distribution, right? So these are the type of questions that we should think about. And in fact, what I'm going to give you is some very simple conditions that under these conditions, the answer to all this question is yes. There either 6, there is only one, and the chain converges to it, right? So the questions are, does a stationary distribution exist, always exist? Second question would be, is it unique? And one that is a little subtle, right? Because you can have 1 and 2 without having this one. You can have a unique stationary distribution, but that doesn't mean that if you start the chain and you take time to infinity or time very large, that you start approaching that stationary distribution, right? Is it approaching the stationary distribution, right? Is it converging? Is the Markov chain converging? So what I mean by that is, for example, if you take the limit as t goes to infinity of let's say pt of phi equals okay, so to answer this question, instead of giving just a dry answer here, let me give you 2 examples of things that could go wrong. But this example are going to be important because these are the only things that could go wrong. Okay, so consider this 2 example here, where you have a disconnected graph, right? Something like this: A, B, C, and D. Right? Suppose that this is your graph, and you're considering the random walk on this graph, right? So now, if you look at the transition matrix, the transition matrix will have, it's a 4x4 matrix, right? A, B, C, and D. A, B, C, and D. The probability of going from A to A is 0, from A to B is 1, from A to C or from A to D is 0. Then from B to A is 1, then 0, 0, and 0. From C to D is 0, and everything else is 1, and everything else is 0. And then from D to C is 1, and every other transition is 0, right? So this is the transition matrix, right? And now, if I take the vector, the distribution 1/2, 1/2, 0, 0, and multiply it by P, what I get is, you can check this, you can get 1/2, 1/2, 0, and 0. Right? So that means that this distribution, 1/2, 1/2, 0, and 0, is a stationary distribution for P. Right? But it's not the only one, because if I do 0, 1/2, 1/2, like this, I get, again, the same vector, which means that this is another stationary distribution, right? So in general, there could be more than one, but you can only have one if you have this kind of pathology in your state space, that you have a disconnection, right? So if your state space is connected, I'm going to formalize that next. If your state space is connected, and something else, but that's a necessary condition. Once you have the space connected, you are going to avoid this kind of pitfall. The other thing that can go wrong is if you have some kind of period in your distribution, this limit may not exist. Okay, so consider a random walk on a bipartite graph. Okay, so okay, you have your bipartite graph like this, and all the edges are like this. Okay? And suppose that at time 0 you started from this side of the graph. Well, then you know that at even times you're always on this side, and at odd times you're always on this side. Right? So if you look at this limit here, right? If you look at the subsequence of even times, it would have a different limiting behavior than the subsequence of odd times, and since these two are different, the limit can exist. Okay, so in a sense, when you have this type of periodicity on when do you return to parts of the state space, this will make the limit to not exist. Okay? This is another important example. Again, and now with these two things, this is everything that can go wrong, right? So the fundamental theorem of Markov chains that I'm going to state next is that if your state space is connected, you don't have this, and you don't have this sort of periodic behavior. If neither of these things happen, then your Markov chain converges to a unique stationary distribution. Okay, so let me state all that with the right mathematical words and so on, so that you guys know what they are, right? So, okay, so here are a few definitions, very simple ones. The first one is irreducible. When the Markov chain is irreducible, well, if the state space is connected. Okay. Now, we have to be a little bit careful what we mean by connected. Remember that the state space, okay, so this is not really what defines, so let's define it properly. We say that for every x and y in omega, there exists t, such that p to the t x y is strictly greater than 0. Okay, so that's exactly what we mean. So if you start from x, there is going to be some time after which you have some chance of getting to y, to any other y. And this needs to hold pairwise. So essentially, when you look at the state, if you look at this representation of weighted graph that we were considering, it means that you can follow the arrows and go from anywhere to anywhere. Okay, so that's what that's what it means, irreducible. The other definition is aperiodic. Which means that in words, I guess the intuition is that if you look at any vertex and you look at all the possible times at which you can return to that vertex, right? There is no pattern, right? It's not like you only get to these vertices at even times, or you only get at these vertices when it's a multiple of 4 or something like that. Right? So let's formalize that. So it is aperiodic. A Markov chain is aperiodic. If for every x, if we consider the set of return times to x, right? So this is the t, such that p to the t from x to x is greater than 0. So this is the set of all the times that, let's say I'm at x and I'm looking at all the times that I can return to x. I look at the greatest common divisor between all of these numbers, and this has to be equal to 1. Okay, so with this condition, with these two conditions, that's all we need, right? If the chain is irreducible and aperiodic, then it converges to a unique stationary distribution. So let me write that. So this is the fundamental theorem of Markov chains. So a Markov chain that is irreducible and aperiodic has a unique stationary distribution and converges to it. Okay, so let's pause here to see if you guys have questions. So this may look like some kind of weird properties, but they're actually quite simple, right? So well, first one is connected, right? You look at the state space, you need to be able to go from anywhere to anywhere. Right? That seems like a reasonable property. The periodic one, the aperiodic one, may look a little bit more unusual to you, but it's actually one that is quite easy to ensure. Okay, so for example, suppose that you have your Markov chain that is already irreducible. You know the state space connected, right? One quick way of ensuring that the Markov chain is aperiodic is by adding a self loop to any state, right? So let's say that you, from state A, you're going to say, look, with probability 1/2, I'm going to stay here, and with probability 1/2, I'm going to do what I was doing before, right? This simple modification to a Markov chain is sufficient to guarantee that it is aperiodic, right? And it really doesn't change any long-term behavior of the, like in terms of the speed of convergence and so on. This is very small delay in one particular state, right? And the intuition why this is true is because, well, if you can go from anywhere to anywhere, you start from X, you get to that vertex that has the self loop, and there you can break any period, right? You can take any number of, you can use the self loop as many times as you want to break any period and then return, right? And then you ensure that the GCD, the greatest common divisor, is 1. Right? Okay, questions? Okay, so I wanted to get, yeah, go ahead.
Can we prove this fundamental theorem of Markov chains, or is it too hard?
It's a little hard. It's not too hard. If this was a full course on MCMC, we would do it, but it would take maybe 1 or 2 lectures just to do it. Okay? It's definitely not a 10-minute proof. Okay, so we will not do it, and we'll take it for granted. Otherwise, the whole 2 lectures would be just proving this. Okay. Actually, in your problem set, I put part of the proof. Right, there is part of the proof of this fundamental theorem as an exercise in your problem set. That is not the bad part of the proof, and you can actually work it out with your TA. Okay. Any other questions? Okay, so now that we have this fundamental theorem of Markov chains, I'm going to define finally what the Markov chain Monte Carlo method is, or a Markov chain Monte Carlo algorithm is. Right. So here it is. So what is the idea, right? Remember the initial problem that we wanted to solve, right? Markov chain Monte Carlo method. So we have some distribution pi over omega, and we want to sample from pi. Okay, so this is the problem from the beginning of the lecture. So how can you do it now using a Markov chain? So the general strategy here is going to be, first, we're going to design a Markov chain pi omega, and that has, so let's call it, the Markov chain is going to be, irreducible and aperiodic. Maybe I should just tell you, I wanted to avoid this, but to avoid just throwing more words on you. But if you read around, you're going to notice that there is this word ergodic, right? And a Markov chain is ergodic if it is irreducible and aperiodic. For some reason, someone decided that let's just have one word for the Markov chains that are irreducible and aperiodic, right? This is an ergodic Markov chain. So if a Markov chain, we're going to design an ergodic Markov chain that converges to our target distribution pi. Right? And then we're going to run the chain or simulate the chain, right, for a long time, whatever that means, and output the state of the chain. Right? And this is the MCMC approach, right? So, okay, questions? Okay, so let me say a few things about it before we move on, right? So usually, okay, so typically, designing the Markov chain is not the hardest problem, right? In fact, once you have a distribution, there are several standard choices of things that you can try to come up with some Markov chain that converges to your target distribution. So the design of the Markov chain, I mean, sometimes, you know, there are very creative Markov chains to circumvent some difficulties and so on, but in general, there's some standard choices that we can try first, okay? The second question is crucial, right? Because this long time, what do we mean by that, right? So what is the reasoning? The reasoning is that since the Markov chain is ergodic, we know that in the limit as it goes to infinity, it converges to the target distribution, right? And the question is, well, how fast is converging? Do we need to take 1,000 steps or 100 steps or 1,000,000 steps, right? So we don't really know the answer to that question, right? And this is a key research question in theoretical computer science, physics, mathematics, other areas, right? You have some Markov chain and you want to understand how many steps you have to take to ensure that your error is less than 5% or less than 1% or less than whatever it is that your application requires. Okay. Now, the one reason why this method is so popular is that to use it, you don't really need to have theoretical guarantees. Okay. Once you design your Markov chain, you can gamble and say, okay, let me try and take 1,000 steps and see what happens. Okay. And yeah, maybe that's good enough. And in many cases, that's good enough. Right? Now, as theoretical computer scientists, what we are interested in, one thing that I'm interested in is analyzing and prove rigorous guarantees and say, look, take 1,000 steps, this is going to be your error, right? Or when you have a Markov chain on a graph, say on the independent sets, take n to the 5 steps, and this is going to be your error, right? So this is the type of questions that we study in theoretical computer science and discrete math about this speed of convergence. Right? But I should emphasize that that's what we do in theory. In practice, there are many Markov chains that are deployed and are useful, and people are getting interesting results with them, and we don't really understand them theoretically. Right? So there is this disparity between what we can prove versus what seems to be good in practice. Right? And yeah, hopefully we can bridge this gap, but definitely practice is moving at a very fast rate. So we are playing catch up, and we have been playing catch up for 20 years, or maybe more, maybe 30 years, and we can't seem to keep up. Okay. Okay. Any questions? There is one more standardization that we need, right? Remember, Markov chains, stationary distribution, the MCMC method. We need a way of measuring convergence, right? We need a way of saying, look, after these steps, you are this far from converging, right? And that's that standardization is the notion of mixing time, right? Which is a key, the next key concept, right? How to measure speed of convergence. Okay, so the key notion here is going to be, let's call it the epsilon mixing time. As I say, this is not the only way of measuring the speed of convergence, but it's the most standard one, right? Okay, so we're going to get a Markov chain. Let be a Markov chain. Okay, and then for x in omega, define the following quantity. Let's call it T mix, this mixing time from x, allowing error epsilon. This is the first time such that the minimum T, such that the distance in some way of measuring distance between the distribution of the chain and the stationary distribution, where we know that the chain is going, is below epsilon, right? So there is some notion of distance between the probability distribution of the chain starting from x and the stationary distribution. And this is measured in a metric called total variation distance, which I will define now. And we say that this is less than epsilon, right? So this is the definition of the mixing time. And just to complement this, if you haven't seen this, so if mu, okay, so where if mu and nu are probability distributions, we have that the total variation distance between the two distributions is essentially half of the L1 norm between the two distributions, right? So it's like 1/2 summation x in omega of mu x minus nu of x. This is 1/2 of the L1. And there's this also interesting property that will come up later, and you can check as an exercise that is also equal. You look at the maximum over all the subsets of the state space, and you look at mu of a minus nu. Okay, so I've shown here lots of things. This is an important notion, right? But the intuition is, look, I want to know the first time that the distribution of the Markov chain is close enough to the distribution, the stationary distribution, right? We know that when it goes to infinity, the distance will be 0. We want to know the first time that the distance is less than epsilon, okay? That first time, yeah, go ahead, Ali, go ahead.
Sorry for interrupting. So this is the first time the error is less than epsilon. But how do we know that the error is not going to increase in the later steps?
That's a good question. There is some monotonicity property here that, again, we will not, I will not prove, but I believe, and now I believe that under some conditions that probably we have them here already, the error will, yeah, actually, yeah, this is, yeah, the error will not increase, okay?
Okay, thank you.
Yeah, so there's some, I mean, I can point you to where to check this, but there is some subadditivity property here of the total variation distance that will ensure, for example, you can boost this to anything you like, right? So let me, okay, I'm almost out of time. So let me just say one more thing here and then expand a little bit on Ali's question because it's a good one, right? So this is called the epsilon mixing time. And what folks call just the mixing time, because maybe you never heard the term epsilon mixing time, but the mixing time, right? It's well, we fix a given epsilon and we take the worst we take the worst possible starting state, right? So we find the mixing time as the maximum x in omega of the mixing time from x, and we take a certain epsilon here, 1/4. The constant is not very important. It has to be less than 1/2, strictly less than 1/2 is good enough, right? And here is the point that I wanted to make from Ali's question is that once you get the distance below 1/4, okay, you can boost it up very easily to make it even much smaller than 1/4, right? To anything that you like. So the idea is that once this total variation distance is less than 1/4. Let's say that you went t steps, right? And the distance less than 1/4. If you go t log of 1/delta, you can make your distance less than the delta, right? So with multiplicative logarithmic factor, you can get a motion-proof error rate, right? So in general, our aim is to theoretically to find the first time that we get below a constant 1/4, because then this is very easy to boost this to error rates of 1/n or 1/n squared, and you only pay logarithmic in 1 over the error rate that you're looking for, right? So maybe Ali, this helps your question, right? Your
Yeah,
concerns,
definitely.
I guess. Right?
Yeah.
So you can boost it up by very cheaply. You can boost it up, right? You pay a small factor and you make the error as small as you like. Right? Okay, so let me just tell you what is next. What we'll do next, right? What is next, and this is something that I spent a lot of time thinking about, is how to bound the mixing time of a chain. So now we have defined a chain, the stationary distribution, when it converges, and this notion of a speed of convergence, right? When is the mixing? What is the mixing time? One is the first time that the distance goes below 1/4, right? And there are two families of techniques here. There are not that many techniques, and that's why theory is here and practice way ahead of us. There are not that many techniques, but the techniques that we have can be roughly grouped in two areas. Some of them are probabilistic techniques, and we'll spend some time with that. And the other type of techniques are more like linear algebra, functional analytical techniques that look at the matrix P and the eigenvalues and the eigenvectors and try to infer information from that. So I'll try to give you in the next lecture a little sample from both if we have time, right? And that way you get a more or less complete picture of the MCMC method in terms of how it works and the theory that we know to prove speed of convergence. Okay, so I'll take more questions here, but I guess you guys have some more activities and I don't want to hold you if you have so much stuff to do, but I'm happy to hang around here and answer questions.
Thank you.
Thank you.
Yeah.
Thank you.
So much.
Yeah, so I had a question. What is the TV distance that you define in the T-mix?
Right, so this is total operation distance, and I define it here, right? So essentially, you look at you look at every element of the theory space, and you look at the difference in the probabilities, right? So it's a very natural notion of distance. Right?
Okay.
It's just that you have it. First, you know, the reason will be clear later. But
okay, thank you.
Yeah.
I also had a question. Is the like the term ergodic related to like ergodic like transformations of measure spaces? Does it have like an analog here? Or,
yeah, I don't know. I don't know. I don't want to give you a I don't know. I'm not sure. Maybe, maybe, but
it seems kind of similar. Like
yeah, it looks. I mean, this is the ergodic theory, and there are definitely some similarities. But what I've learned is that sometimes we borrow these terms because they look similar, right? And they're not exactly the same. So,
right. Thank you.
okay, if there are no more questions, then you guys Friday.
Thank you.